Alright guys, we're going to continue to work with radicals. In the previous video we were always working with square roots, so our index was always 2. But the whole process for entire and mixed radicals works regardless of what the index is. We just have to make sure that we are finding perfect roots of that given index. So for example, if I've got something like the cubed root of 81 as my entire radical, I can change that into a mixed by simply splitting into its factors. So for 81, I know that it has a perfect cube 27 as one of its factors, and 27 times 3 would still give me 81. So that allows me now to split my radical into the cubed root of 27 times the cubed root of 3. And the cubed root of 27 is 3, and then it becomes 3 times the cubed root of 3. Okay, so similar to how we did with square roots, we just have a different index. Okay, now I can do that with any index, so I'll just throw in a 5, and let's find the fifth root of 128. We'll change that from entire into mixed. So for that one, the fifth root of, so I need something that's a perfect fifth. So chances are as your index gets higher, if you're working with these, it's a good bet that you're going to be pulling out a 2 or a 3. So 32 is a perfect fifth because it's 2 times 2 times 2 times 2 times 2. And then my remaining factor would be 4. So I now have the fifth root of 32 times the fifth root of 4. And that's going to become 2 times the fifth root of 4. Okay. Now, one interesting thing that we can do with these ones that we couldn't do when it was perfect, or sorry, when we're taking the square root of something, is I might have a negative as part of my radicand. Now, I'm allowed to have a negative under the radical sign so long as my index is odd. So this one, the index is 3, so having a negative underneath the radical sign is fine, because I can have 3 things multiplying together to give me something negative. There is no way to have a negative under the square root symbol if, or sorry, under the radical symbol if our index is even. So with an odd index, negatives are fine, even index, no. So for 24, that one has a nice perfect cube of -8, and that would be times 3. So that would give me then the cubed root of -8 times the cubed root of 3, and the cubed root of -8 is -2. Okay, so again, negatives are allowed if my index is odd. Okay, we'll do a couple where we go from mixed back into entire. Okay, so like we did with an index of 2, I have to take this 1/2 and I need to put it underneath of a cubed root symbol. In order for me to put it under a cubed root symbol, I have to first raise it to an exponent of 3. So I'm going to take that 1/2 and I'm going to raise it to an exponent of 3. So I'm going to cube it, and then at the same time take the cubed root of it. That way it is still right now equal to 1/2. Okay, I have to keep the same value. And then I'm still multiplying by the cubed root of 160. Okay, so that gives me now the cubed root of, and 1/2 cubed is the same thing as 1/8. So I get the cubed root of 1/8 times the cubed root of 160. And that's going to be the cubed root of 160/8, which is really the cubed root of 20. Okay, do another one, different index. Let's go 3 times the fourth root of 2. Sorry, I guess I should do a better job. I'll keep my index and my coefficient a little bit more separated like that. Okay, so to get 3 underneath that fourth root symbol, I need to raise 3 to an exponent of 4, and then I can put it under the fourth root. So I get 3 exponent of 4 and the fourth root of that times the fourth root of 2. So that's going to give me the fourth root of 81 times the fourth root of 2, and that's going to be the fourth root of 162. Okay, like we just said in our on our last page here, if I had something that is negative, so if I've got negative 4 and then the cubed root of 6, I am allowed to bring this negative underneath the radical sign because the index here is a 3. Okay, so the negative is allowed to move underneath the radical sign because I have an odd index. All right, so I have the cubed root of negative 4 cubed times the cubed root of 6, and that gives me the cubed root of negative 64 times the cubed root of 6, and in total that gives me the cubed root of negative 384. Okay, now if I had switched this and if I had done the fourth root instead, the negative would have to stay at the front, and I would simply put the 4 underneath the radical symbol, but the negative has to stay in front. Okay, so you could keep going with that one, and the negative has to live out front because I have an even index, so it's not allowed to move underneath. Okay, now these things also work with variables as well. So this one's listed as an extension in your book, but really I almost find doing this with variables is easier than trying to work with numbers, because it's much easier to see whether or not you've got perfect squares for your exponents on a variable than it is to know all of the different perfect square factors that you can possibly pull out. So for example, if I had something like this, x exponent 7, sorry, that did not work out as planned. If I had something like the square root of x exponent 7 times y exponent 6, I can pull these apart because I have factors of x and y. Okay, so let's say I was to split this, and I would took out x with an exponent of 6 times x. That's another way of writing x exponent 7. Okay, and then the y exponent 6 I can just leave there. Now this is helpful because both x exponent 6 and y exponent 6 are perfect squares, and they're perfect squares because their exponents are even. Right, so x exponent 6 is the same thing as x exponent 3 times x exponent 3, right? So because x exponent 6 can be written as 2 of the same factor multiplying by itself, it is a perfect square. So I'm going to rewrite this as x exponent 6 times y exponent 6 times the square root of x. Now the square root of x exponent 6 is x exponent 3, and likewise it's y exponent 3, and then it's multiplying by the square root of x. Okay, so I always find it easier to pull out variables because I don't actually need to know all of the different perfect squares. I just need to know, is the exponent divisible by the index. Okay, so if you look back, the square root means I've got an index of 2, and my exponent of 6 is a multiple of 2, so it is divisible by 2, and that's why I was able to pull those out. Okay, all right, let's look at a couple more quick ones because I know you'll see a few in your book, so just so you've got some examples to go from. Let's say I had the square root of 18x exponent 5, so now I'm mixing in my coefficients and variables. So with this one, I could pull out a 9 times 2 because 9 is a perfect square, and for x, I could get x exponent 4 times x. So in this one, now I've got 9 and x exponent 4 are my perfect squares. So that gives me now the square root of 9x exponent 4 times the square root of 2x. The square root of 9 is 3. The square root of x exponent 4 is x squared. Just divide the exponent by the index of 2. And then we're still multiplying by the square root of 2x. Okay, and I can work backwards as well. I can take those and I can put them back from mixed into entire. So if I had something like a times the square root of a, okay, then I could simply take a, and I got to put it under a square root symbol. And if I do that, that means I also have to square it. I have to make sure my index and my exponent match. and then I'm multiplying by the square root of a, so in total that becomes the square root of a squared times a, and that's the square root of a cubed. Okay, and if I was to do one that had a coefficient as well, so let's say I was working with 3x cubed multiplied by the square root of xy, this would then become 3x cubed, and I would need to square that and then square root it so that it still has the same value multiplied by xy, and that's going to give me the square root of 3 squared is 9, x cubed is x exponent 6, and then I'm going to multiply by the xy, and that gives me the square root of 9x exponent 7y. Okay, and it does work even if we switch up the index where it's not an index of 2. So let's say I had something like the fourth root of x exponent 11 times y exponent, let's pick 19, or no, we'll pick 17. That sounds more fun. Okay, so with this one now, I need to make sure that I'm pulling out perfect fourths, and the way I'll know it's a perfect fourth is if the exponent is divisible by 4. Okay, so x with an exponent of 11, 11 is not divisible by 4, so the closest multiple of 4 would be x exponent 8, and then I would also still need to be multiplying by an x exponent 3, so that in total I still have that exponent of 11. For y, I could get 16 times y, and so now I've got it written where my two perfect fourths are x exponent 8 and y with an exponent of 16, and they are perfect fourths because both are divisible by 4. Okay, so I should put the fourth root in front, otherwise that totally changes what we're doing. So I have then the fourth root of x exponent 8, y exponent 16, and that is multiplying by the fourth root of x cubed, y, and that leaves me with, so for this one, x exponent 8, the fourth root, so I need to divide the 8 by 4, gives me x exponent 2, y exponent 4 times, and then the fourth root of x cubed y. And we'll talk more about this in a video in a couple of weeks, and we'll kind of look at working with radicals and changing the way we write radicals so that we can actually use an exponential form instead of needing to write the radical sign every single time. Alright, so there's converting mixed and entire radicals when we're working with different indexes, or indices, if you will. Bye.